Okay, so get this.
Okay.
Imagine electronics that are lightning fast
Yeah.
because they have zero resistance.
Wow.
We're talking superconductors. And a recent discovery in the quantum realm might bring us closer to that reality. We're going deep on a research article called Quantum Breakthrough Could Propel Superconductors to the Next Level.
Okay.
To see just how big a deal this is.
I'm ready.
At the heart of this are Kagome magnets.
Right.
These materials have a unique structure.
Interesting.
Inspired by ancient Japanese basket weaving.
Oh, wow.
But what makes them truly fascinating is how this structure leads to some bizarre, even unexpected behavior at the quantum level, especially when it comes to magnetism. Researchers at Rice University took a closer look at a specific Kagome magnet called iron tin, or Fes.
Got it.
They used a two-pronged approach to study it.
Interesting.
First, they grew ultra-pure thin films of Fes, using a technique called molecular beam epitaxy. Think of it like building a perfectly ordered Lego structure atom by atom.
Wow, that's precise.
Then they used angle-resolved photoemission spectroscopy, or RPs, to analyze how light interacts with the electrons in Fesen.
Okay.
Kind of like taking a snapshot of the electrons in action. And this is where things get interesting.
Okay, tell me more.
You see, conventional wisdom said that the magnetism in these materials comes from freely moving electrons.
Right.
What we call itinerant electrons.
Yeah.
But the RP's data revealed something totally unexpected.
Really?
What did they find?
So the magnetism in Fesen is actually driven by localized electrons, meaning electrons that are stuck in a specific location within the material. It's a huge paradigm shift because it challenges our fundamental understanding of how magnetism works in these materials.
It's like finding out the Earth is flat. It completely changes our whole perspective.
Exactly. It's a game changer. And there's more.
Okay.
Remember those unique Kagome structures we talked about? Well, they create something called flat bands, which are essentially electron highways that can lead to some unusual electronic behavior.
I see.
The research showed that these bands stay split even at higher temperatures. And this is directly related to those localized electrons being the drivers of the magnetism.
So we've got these flat bands created by the Kagome structure.
Right.
And they're somehow connected to these localized electrons that are doing something completely unexpected.
Exactly.
Where does this lead us?
Well, remember how we talked about superconductors at the beginning?
Yes.
Flat bands are considered crucial for achieving high-temperature superconductivity, which is the holy grail of superconductor research.
Right.
If we can make superconductors work at more practical temperatures, it would revolutionize everything from electronics to energy.
Okay, so this research on Fes, with its localized electrons and flat bands, could hold the key to unlocking that potential.
It could?
That's huge.
It is.
Ah.
And there's another intriguing detail that emerged from this research.
Okay, what's that?
They found something called selective band renormalization in Fesen.
Now that sounds complicated.
It's not as bad as it sounds.
Break it down for us.
Think of it like this.
Okay.
Imagine a group of friends walking down a crowded street.
Okay.
Some friends might get separated from the group because of the crowd, while others manage to stick together.
Okay, I see where you're going with this.
Right.
So in Fesen, the researchers found that some electron orbitals were more strongly affected by interactions than others.
Yeah. Similar
to how some friends might get separated in the crowd.
Exactly.
So some of the electrons are getting pushed around more than others.
Right.
And that's important because
it suggests that these interactions play a crucial role in shaping the electronic and magnetic properties of the material.
Okay.
What's even more interesting is that this phenomenon, this selective band renormalization, has also been observed in iron-based superconductors.
Interesting.
Which are a completely different type of material.
Hold on, you're telling me there's a connection between these Kagome magnets and existing superconductors?
That's exactly what this research suggests.
Wow.
And this unexpected connection could lead to a whole new understanding of how superconductivity works, potentially paving the way for new breakthroughs in the field.
This is starting to sound like we've stumbled onto something truly groundbreaking.
It is pretty remarkable.
We've gone from ancient basket weaving patterns to potentially revolutionary technologies.
I know, it's fascinating, isn't it?
And the implications don't stop there.
Oh, there's more.
This research could also have a major impact on a field called topological quantum computation.
That's right.
Okay, now we're getting really futuristic. What is topological quantum computation?
Okay.
And how do Kagome magnets fit into it?
Imagine a computer that can perform calculations in ways that are currently impossible. A computer that harnesses the bizarre laws of quantum mechanics to its advantage.
Okay.
That's the promise of topological quantum computation.
So it's like the next level of computing power. It's powered by quantum weirdness.
Precise.
And the unique properties of Kagome magnets.
Right.
Especially their ability to host these exotic electronic states, make them ideal candidates for building the components needed for this type of quantum computer.
That's the idea.
Wow. So we've got potential advancements in superconductors, quantum computers.
It's exciting stuff.
Where does it end?
The possibilities truly are mind-boggling.
But before we get too carried away, let's bring it back down to Earth for a moment.
Okay.
You mentioned that this research could have a major impact on our everyday lives.
Yeah.
Can you give us some concrete examples?
Sure.
How could this research actually change the world as we know it?
Well, let's start with energy.
Okay.
Imagine a world where we can transmit electricity with virtually no loss thanks to high-temperature superconductors.
Okay.
Power grids would become incredibly efficient, reducing our reliance on fossil fuels and paving the way for a cleaner, more sustainable future.
That sounds amazing.
It does, doesn't it?
No more worrying about blackouts or energy shortages.
Right.
But what about other areas?
Transportation is another area ripe for disruption.
Okay.
Superconducting magnets could lead to the development of levitating trains that travel at incredibly high speeds, revolutionizing how we get around.
Wow.
And in the realm of medicine,
Okay.
imagine MRI machines that are far more powerful and precise thanks to the unique properties of Kagome magnets.
So we're talking about potentially life-changing advancements in healthcare, transportation, and energy.
We are.
It's incredible to think that all of this could stem from studying these strange materials.
It really is.
And remember, these are just a few examples.
Yeah, just scratching the surface.
As we continue to delve deeper into the world of Kagome magnets, who knows what other applications we might discover?
Exactly. The possibilities are endless.
It feels like we've only just begun to scratch the surface of what's possible.
I agree.
But let's not get ahead of ourselves.
Right.
We're just at the beginning of this journey of discovery. Before we explore the full potential of Kagome magnets, we need to understand exactly how they work.
Absolutely.
Okay, let's do it. Take us back to the lab.
Let's go.
How did the researchers actually make these discoveries?
Yeah.
What were the key techniques and findings that led to this groundbreaking revelation?
Well, it all starts with those two techniques I mentioned earlier.
Okay.
Molecular beam epitaxy and angle-resolved photoemission spectroscopy.
Right. Those are the tools they used to study FESN.
Yeah.
But what exactly did they reveal about this material that led to the surprising conclusion about localized electrons?
Let's break it down.
Okay.
Remember, molecular beam epitaxy allowed the researchers to create these incredibly pure and well-ordered thin films of FES, essentially building the material atom by atom.
Right.
This level of precision is crucial because it eliminates impurities and defects that could obscure the intrinsic properties of the material.
So it's like creating the perfect canvas for their scientific masterpiece.
Exactly.
And once they had this pristine canvas, they used ARPs to take a close-up snapshot of the electrons in FESN, revealing their energy and momentum.
Okay.
This is where the magic happened.
Right.
The ARP's data showed that the electrons responsible for the magnetism in FESN weren't the freely moving itinerant electrons that everyone expected.
That's right.
Instead, they were localized electrons stuck in specific locations within the material.
It was a huge surprise.
It's like finding out that the engine of a car you thought was electric is actually powered by steam.
I love that analogy.
This unexpected finding challenged the prevailing paradigm of magnetism in Kagome magnets.
It did.
Forcing scientists to rethink their understanding of how these materials work at the most fundamental level.
Forcing everyone to go back to the drawing board.
And it was all thanks to these powerful techniques that allow researchers to peer deep into the quantum world of FESN.
That's right.
But the story doesn't end there.
It doesn't.
The researchers went even further, exploring the concept of selective band renormalization. Yes, the friends on a crowded street analogy.
Yeah.
But can we dig a little deeper into that? How does that concept relate to the electron orbitals and their interactions in FESS?
Okay, so you see electrons in a material occupy different energy levels. Kind of like floors in a building.
Yeah.
And each electron orbital corresponds to a specific energy level.
So we're picturing electrons on different floors of this building.
Right.
Okay.
Now imagine that some floors are more crowded than others.
Yeah.
And the people on those floors are bumping into each other more frequently. That's similar to what's happening with selective band renormalization.
So those crowded floors represent electron orbitals that are experiencing more interactions.
Exactly.
And this bumping is actually affecting their energy levels.
That's right.
And this is significant because
it suggests that these interactions play a crucial role in shaping the electronic and magnetic properties of Kagome magnets.
Okay.
And remember, we've seen similar selective band renormalization in iron-based superconductors. This unexpected connection opens up a whole new avenue for research, potentially linking to seemingly unrelated fields.
It's like finding a secret passageway connecting two different worlds.
I like that.
And exploring this connection could lead to new breakthroughs in both superconductivity and quantum computing.
That's the hope.
Okay, so we've covered the basics of Kagome magnets.
Yeah.
The surprising findings of this research, and the potential implications for future technologies.
Right.
But let's get even more specific.
Okay.
What are some of the potential applications of Kagome magnets that we might experience in our lifetimes?
One of the most exciting potential applications is in the field of high-temperature superconductivity.
Right.
Materials that can conduct electricity with zero resistance, meaning no energy is lost as heat.
It's like having a power grid that never loses any electricity.
Exactly.
Imagine the energy savings.
It could be huge.
But current superconductors require extremely low temperatures to function.
Right.
Which makes them impractical for many applications.
Yeah. That's the problem.
That's where Kagome magnets come in.
That's right.
Because their unique electronic properties, especially those flat bands we talked about, make them promising candidates for achieving high-temperature superconductivity.
Precisely.
If scientists can unlock the secrets of superconductivity in Kagome magnets, it could revolutionize everything from energy transmission and storage to transportation and medical imaging.
Absolutely.
It sounds like something straight out of a science fiction novel.
It does, doesn't it?
But how would that actually work? What kind of real-world applications are we talking about?
Well, imagine a world where power lines can transmit electricity with 100% efficiency.
Okay.
Eliminating energy loss and dramatically reducing our carbon footprint.
Wow.
Or picture levitating trains that glide effortlessly above the ground, powered by superconducting magnets.
Those are some game-changing applications.
They are.
And what about medical imaging?
Yeah.
You mentioned that Kagome magnets could lead to advancements in that area as well. How so?
MRI machines, for example.
Okay.
Rely on powerful magnets to create detailed images of the inside of the human body.
Right.
But current MRI machines have limitations.
I see.
Kagome magnets, with their unique magnetic properties, could lead to the development of more powerful and precise MRI machines, enabling doctors to detect and diagnose diseases at earlier stages.
So we're talking about potentially life-saving advancements in healthcare.
We are.
It's amazing to think that all of this could stem from studying these seemingly obscure materials.
It is.
And remember, these are just a few examples.
Right.
As we continue to explore the world of Kagome magnets, who knows what other applications we might discover?
Exactly.
It's a future filled with possibilities.
It is.
But let's not forget the other major area. You mentioned quantum computing.
Yeah.
You said that Kagome magnets could play a key role in developing this revolutionary technology.
That's right.
Can you elaborate on that?
Quantum computers operate on the principles of quantum mechanics, which are vastly different from the classical physics that govern our everyday world.
Right. Quantum mechanics is the realm of the very small.
Yes.
Where things behave in strange and counterintuitive ways.
Exactly.
And quantum computers take advantage of these bizarre quantum phenomena to perform calculations in ways that are currently impossible for even the most powerful classical computers.
That's right.
I've heard that quantum computers have the potential to solve problems that would take classical computers billions of years to solve.
That's true.
So where do Kagome magnets fit into all of this?
Building a quantum computer is incredibly complex.
Right.
It requires creating and controlling something called qubits.
Okay.
Which are the quantum equivalent of bits in a classical computer.
And qubits are these strange entities that can exist in multiple states at once, right?
Exactly.
And that's where Kagome magnets come in.
That's right.
Their unique magnetic and electronic properties.
Yeah.
Especially their ability to host those exotic electronic states we talked about, make them potential building blocks for creating robust and stable qubits.
Precisely.
So Kagome magnets could hold the key to unlocking the power of quantum computing.
They could.
And that's not all.
Nope.
Kagome magnets also hold promise for applications in spintronics.
They do.
A field that explores the use of electron spin for information processing and storage.
It's a fascinating field.
It sounds like Kagome magnets are the key to a whole new technological era.
They have the potential to be.
And this is just the beginning.
Oh yeah, we're just getting started.
As researchers continue to explore the strange and wonderful world of Kagome magnets, we can expect to see even more groundbreaking discoveries and technological innovations in the years to come.
I agree.
It's an exciting time to be alive.
It is.
But before we get lost in the possibilities of the future,
right,
let's take a moment to appreciate the journey that led to this incredible discovery.
Okay.
What were some of the key challenges that researchers faced in studying FESS?
Well, one of the biggest challenges was creating those ultra-pure, well-ordered, thin films of FESS using molecular beam epitaxy.
Right.
It requires incredibly precise control over the growth process.
Okay.
Ensuring that each atom is placed exactly where it needs to be.
It's like building a microscopic Lego structure, but with atoms instead of bricks.
Exactly.
And then there's the challenge of interpreting the EPS data.
Right.
It's a very complex technique that requires a deep understanding of quantum mechanics and solid-state physics.
It is.
So it's not just about collecting the data, but also about deciphering its meaning and extracting the hidden secrets within it.
That's a great way to put it.
And in this case, the ABPS data revealed something truly unexpected.
Yes, it did.
The magnetism in FESS wasn't coming from the usual suspects,
right,
the freely moving electrons.
Yeah.
Instead, it was driven by those localized electrons.
That's right.
Which challenged the prevailing theories about how magnetism works in Kagome magnets.
A real paradigm shift.
It's a reminder that science is a process of constant discovery.
Absolutely.
Of questioning our assumptions and being open to new possibilities.
A great reminder.
And this discovery wouldn't have been possible without the dedication and ingenuity of the researchers who dared to explore the unknown.
True, they were real pioneers.
They were true pioneers venturing into the uncharted territory of the quantum world.
Exactly.
And their journey has just begun.
It has.
As we continue to unravel the mysteries of Kagome magnets, who knows what other wonders we might uncover.
So many possibilities.
What other hidden truths are waiting to be revealed.
Who knows, but it's exciting to think about.
It's a thought that leaves me both humbled and incredibly excited for what the future holds.
I feel the same way.
But before we dive into those future possibilities, let's take a closer look at the present.
Okay.
This research on FESS is groundbreaking.
Yeah.
But it's important to remember that it's just one piece of a much larger puzzle.
That's right.
There's still so much we don't know about Kagome magnets.
So much to explore.
So what are the next steps in this research?
Yeah, that's a great question.
What are the key questions that scientists are now grappling with?
Well, one of the biggest questions is whether this discovery about localized electrons in FESS holds true for other Kagome magnets.
Okay.
Do they also exhibit this unusual form of magnetism?
So it's a matter of seeing if this is a unique quirk of FESS or a fundamental property of Kagome magnets in general.
Exactly.
And if it turns out to be a more general phenomenon,
right,
it could have profound implications for our understanding of these materials and their potential applications.
Absolutely.
So it's back to the lab.
Back to the lab.
Back to the drawing board.
Yeah.
To see if this discovery holds up under further scrutiny.
We need more data.
And then there's the question of how to harness the unique properties of Kagome magnets for practical applications.
Ah, yes. The big question.
Right. We've talked about the potential for high-temperature superconductivity, quantum computing spintronics.
All those exciting possibilities.
But how do we actually go from these theoretical possibilities to real-world devices?
That's where the real challenge lies.
And what does that challenge look like?
It requires a deep understanding of the fundamental physics of these materials.
Okay.
As well as the development of new fabrication techniques and engineering solutions.
So it's a multidisciplinary effort.
It is.
Bringing together physicists, chemists, engineers, and material scientists to push the boundaries of what's possible.
A real team effort.
It's a team effort, a testament to the collaborative nature of scientific discovery.
Couldn't have said it better myself.
And it's a journey that promises to be as exciting as the destination itself.
I agree.
Well, that's a thought to leave our listeners with.
It is a good one.
But before we get too carried away,
right,
let's take a step back and consider the broader context of this research.
Okay.
We've talked a lot about the potential benefits of Kagome magnets.
Yeah, the possibilities are truly amazing.
But are there any potential downsides or risks that we should be aware of?
That's an important question to consider.
What are your thoughts on?
As with any new technology, there are always potential risks and ethical considerations that need to be carefully addressed.
So it's not just about the what, but also the how and the why of technological advancements.
Exactly.
And as we explore the potential applications of Kagome magnets, it's crucial that we do so responsibly and ethically.
I agree.
Ensuring that these technologies benefit humanity as a whole.
That should be the goal.
That's a great point.
It is something to keep in mind.
We can't let the excitement of scientific discovery blind us to the potential consequences of our actions.
You're absolutely right.
So for our listeners who are eager to delve deeper into the world of Kagome magnets and quantum materials, where should they go?
Let me think.
What resources would you recommend?
There are some fantastic online resources available.
Okay, that's just.
The website of the Rice University Research Group that conducted this study is a great starting point.
Okay.
They have published several papers and articles that explain their work in more detail.
Excellent recommendation.
Thanks.
And for a broader overview of quantum materials, are there any other websites or organizations that you would suggest checking out?
The website of the Institute for Quantum Information and Matter at Caltech is a treasure trove of information.
Those are some great starting points.
Oh, cool.
And of course, there are countless books and articles on quantum mechanics, superconductivity, and quantum computing.
There are.
But be warned, some of these topics can get pretty complex.
Yeah, they can.
But don't let that intimidate you.
Don't be scared.
There are many resources geared towards a general audience.
There are.
And remember, even experts were once beginners.
That's true.
Exactly. The journey of discovery is just as rewarding as the destination.
I agree.
So embrace your curiosity and keep exploring the fascinating world of science.
Well said.
Well said.
And who knows? Maybe one of our listeners will be the one to make the next breakthrough in Kagome magnet research.
That would be incredible. But for now, we've reached the end of part 1 of our deep dive into the fascinating world of Kagome magnets.
Okay.
In our next segment, we'll delve deeper into the specifics of Kagome magnets, their unique properties, and how they might revolutionize the world as we know it.
Sounds good.
So stay tuned for part 2 of our deep dive into the fascinating world of Kagome magnets.
We'll be right back. Welcome back. So before the break, we were talking about how this research on FSN could revolutionize everything from energy transmission to quantum computing.
It really could have a huge impact.
But let's step back for a moment and really try to understand what makes Kagome magnets so unique.
All right, let's dive into that.
Okay, so Kagome magnets.
Right.
What sets them apart from other magnetic materials?
Well, it all comes down to their structure.
Okay.
Imagine a lattice of atoms arranged in this specific pattern, inspired by those ancient Japanese basket weaving techniques.
Okay.
This pattern creates these triangles interconnected with each other, forming this kind of geometric web.
I'm picturing it in my head.
It's almost like a honeycomb, but with triangles instead of hexagons.
That's a great way to visualize it.
And this unique triangular arrangement of atoms leads to some truly bizarre and unpredictable electronic behaviors.
Right.
Like the electrons are navigating this complex maze.
I like that analogy.
And their interactions within this maze give rise to all sorts of exotic phenomena.
Exactly.
So the geometry of the Kagome structure is the key.
It really is.
It's like the architecture of the material is dictating how the electrons behave.
That's a great way to put it.
And one of the most intriguing consequences of this unique structure is the emergence of those flat bands we've been talking about.
Right, those flat bands.
Right, the electron highways that could lead to high-temperature superconductivity.
Exactly.
Can you remind us why these flat bands are so important?
Sure. So imagine a typical highway with cars moving at different speeds.
Okay.
Some cars are zipping along in the fast lane while others are stuck in traffic. Now imagine a highway where all the cars are forced to travel at the same speed. That's what's happening in a flat band.
Interesting.
The electrons are all moving with the same energy, which makes them behave in a very unusual and coordinated way.
So it's like synchronizing the movement of all the electrons, forcing them to work together in a way they normally wouldn't.
Exactly.
And this synchronized behavior has some profound implications.
It does.
For example, it can lead to enhanced interactions between electrons.
Right.
Which, as we discussed earlier, is crucial for achieving high-temperature superconductivity.
Exactly.
Okay, I'm starting to see the connection.
Yeah.
The Kagome structure creates these flat bands, which force the electrons to behave in a more synchronized way. And this synchronized behavior could lead to the emergence of superconductivity at higher temperatures.
That's the idea.
It's all starting to click into place.
I'm glad to hear that.
But remember, we're still in the early stages of understanding Kagome magnets. There's a lot more research to be done.
A lot more.
Before we can fully harness their potential.
Absolutely.
That's true.
Yeah.
But even in these early stages, the possibilities are truly mind-boggling.
They are. It's an exciting field.
It feels like we're on the verge of a new era of technological innovation driven by these strange and wonderful materials.
I agree. It's a very exciting time for this area of research.
And it's important to remember that this research on FESN is just one piece of a much larger puzzle.
It is.
There are many other Kagome magnets out there.
Oh, yeah. Tons.
Each with its own unique properties and potential applications.
Right. Different structures, different properties, different possibilities.
So there's a whole world of Kagome magnets waiting to be explored.
There is. It's like a whole new frontier of material science.
And each new discovery has the potential to unlock even more incredible possibilities.
Exactly. We keep finding new and surprising things all the time.
For example, researchers are exploring Kagome magnets.
Right.
For use in spintronics.
That's right.
Which is a field that exploits the spin of electrons for information processing and storage.
A very promising area of research.
Okay, that's a new one.
Okay.
Spintronics.
Yeah.
What can you tell us about that?
Think of it this way.
Okay.
In traditional electronics, we use the charge of electrons to carry information.
Right, like the flow of electrons in a circuit.
Exactly. But electrons also have an intrinsic property called spin, which can be thought of as this tiny magnetic moment.
Like a tiny little magnet attached to each electron.
Yeah, that's a good way to think about it.
So in spintronics, we use the spin property to store and manipulate information.
Exactly.
So instead of just using electrons as tiny charges, we're also using them as tiny magnets.
That's right.
And Kagome magnets, with their unique magnetic properties, are ideal candidates for developing spintronic devices.
They are a perfect match for this kind of technology.
I'm starting to see a pattern here.
What's that?
It seems like Kagome magnets are this incredibly versatile platform.
Oh, they are.
For exploring all sorts of new technologies. From superconductors to quantum computers to spintronics.
It's amazing how many different fields they have potential applications in.
Their unique structure and electronic behavior make them incredibly versatile and promising for a wide range of applications.
It's like they were designed for this kind of cutting-edge research.
It's almost like nature has handed us this incredible gift.
I like that.
This material with the potential to revolutionize so many different fields.
It's a gift that keeps on giving with each new discovery.
And it's our job as scientists and engineers to figure out how to unwrap this gift and put it to good use.
Absolutely. We have a lot of work to do, but it's exciting work.
So let's talk about how we do that.
Okay.
What are the next steps? What are the key challenges that need to be overcome to bring these Kagome magnet-powered technologies to reality?
One of the biggest challenges is understanding the intricate interplay between structure magnetism and electronic behavior in Kagome magnets. Okay. We need to develop a deeper understanding of how those triangular lattices of atoms, those flat bands, and those localized electrons all work together to create the unique properties that we're so excited about.
It sounds like we need to map out the entire landscape of Kagome magnets.
We do.
Exploring their diverse properties. And figuring out how to fine-tune them for specific applications.
Exactly like creating a roadmap for Kagome magnet research.
And that's where advanced experimental techniques and theoretical modeling come into play.
That's right. We need both.
We need to develop new tools and methods to probe these materials at the atomic level.
To really see what's going on.
To see how their structure and behavior change under different conditions.
Exactly.
So the combination of experimentation and theoretical modeling.
It is.
Working together to unlock the secrets of Kagome magnets.
A powerful combination.
And as we gain a deeper understanding of these materials, we can start to engineer them for specific applications.
That's the goal.
For example, if we want to develop high-temperature superconductors, we need to figure out how to enhance the interactions between electrons in Kagome magnets. Perhaps by tweaking their structure or composition.
Exactly. We need to find ways to optimize their properties.
It's like we're playing with a set of Legos.
I like that analogy.
Trying different combinations and seeing what works best.
Exactly. It's all about experimentation and finding the best configurations.
And as we get better at playing with these quantum Legos,
Haha, I love that term, quantum Legos.
We'll be able to build increasingly complex and sophisticated devices.
That's the hope. We're always pushing the boundaries of what's possible.
It's a truly exciting prospect.
It is. It feels like we're on the cusp of something truly revolutionary.
But as we venture deeper into this uncharted territory, it's important to remember that we're not just dealing with scientific challenges, but also with ethical considerations.
That's a very important point.
That's right. As with any powerful technology, it's crucial to think carefully about the potential societal impacts.
We need to be mindful of the consequences.
And ensure that these advancements are used for the benefit of humanity.
That should be the guiding principle for all scientific progress.
So it's not just about pushing the boundaries of what's possible.
No.
But also about doing so responsibly and ethically.
Absolutely. We need to proceed with caution and wisdom.
Okay, let's talk about that.
Okay.
What are some of the ethical considerations that we need to keep in mind as we develop Kagome magnet-based technologies?
Well, one major concern is the potential for job displacement.
Oh, right.
As these technologies automate various tasks and processes, it's important to think about how to support workers who may be affected by these changes.
That's a valid concern.
It is something we need to address proactively.
We need to ensure that technological progress doesn't leave anyone behind.
I agree. We need to find ways to create new opportunities for those who are displaced.
And then there's the issue of access and equity.
Right.
We need to make sure that these technologies are available and affordable to everyone.
To everyone, not just a select few.
Not just those who can afford them.
Exactly. It's about ensuring that the benefits of these advancements are shared by all.
It's about creating a more equitable and just society.
That's right.
And then there are concerns about privacy and security. As we develop increasingly sophisticated technologies, it's crucial to consider how to protect personal data.
Absolutely.
And prevent misuse.
We need to build in safeguards from the beginning.
Those are all valid concerns.
They are complex issues, but we need to address them head on.
It seems like we're at a crossroads. Where we have this incredible opportunity to create a better future.
We do.
But we need to do so carefully and thoughtfully.
With wisdom and foresight.
Considering not just the technological advancements themselves, but also their broader societal implications.
Exactly. It's about the big picture.
So it's not just about the science and engineering, but also about the ethics and the social impact.
It's about creating a future that works for everyone.
You're absolutely right.
We need to have these conversations now before these technologies become widespread.
We need to have open and honest conversations about the potential risks and benefits of these technologies involving not just scientists and engineers, but also policymakers, ethicists, and the public at large.
It's a collective responsibility.
It's a reminder that scientific progress is not just about making discoveries.
No, it's about more than that.
But also about engaging in dialogue. Considering different perspectives.
Absolutely.
And working together to create a future that benefits everyone.
A future that we can all be proud of.
Well said.
Thank you.
So what can our listeners do to stay informed and engaged in this conversation?
That's a great question.
What would you suggest?
There are many ways to get involved.
Okay. Such as?
Follow the work of research groups and organizations that are at the forefront of Kagome magnet research.
Like the ones we mentioned earlier.
Exactly.
Read articles and books on the topic.
There's a lot of great information out there.
And most importantly,
yes, this is key.
Engage in conversations.
With people you know.
With your friends, family, and community.
Right.
About the potential impacts of these technologies. And how we can ensure that they're used responsibly and ethically.
It's about having these conversations and raising awareness.
Those are great suggestions.
I hope so.
We need to be informed, engaged, and proactive in shaping the future that we want to create.
Exactly. We all have a role to play.
Now let's talk about the specific challenges involved in creating these Kagome magnet-based devices.
Okay, let's get into the nitty-gritty.
What are the hurdles that scientists and engineers are currently facing?
One major challenge is scalability. Right now, we can create these unique Kagome structures in the lab.
Right, in small quantities.
Yeah, but producing them on a large scale for commercial applications is a whole other ballgame.
So it's like going from baking a cake in your kitchen to mass producing them in a factory.
Exactly. The principles are the same.
Yeah.
But the scale is vastly different.
We need to figure out how to scale up production without sacrificing precision and quality.
That's right. It's a delicate balance.
And then there's the challenge of integration.
Ah, yes, integration.
Integration, what do you mean by that?
Well, imagine you've created this amazing new superconducting material based on Kagome magnets.
Right.
You still need to figure out how to integrate it into existing technologies.
Right.
Or create entirely new devices that can take advantage of its unique properties.
So it's not just about creating the material, but also about figuring out how to make it work in the real world.
Exactly. It's about bridging the gap between the lab and the marketplace.
And that requires collaboration.
It does.
Between scientists, engineers, and designers
to
develop innovative solutions.
To bring these technologies to life.
It's a multidisciplinary challenge that requires a diverse range of expertise.
Couldn't agree more. It's a team effort.
And then there's the challenge of stability and reliability.
Right.
These Kagome magnet-based devices
Yeah.
need to be robust and long-lasting.
They do.
Capable of operating under various conditions without degrading or malfunctioning.
Exactly. They need to be able to withstand the rigors of the real world.
So we need to ensure that these new technologies are not just cutting edge, but also dependable and practical for everyday use.
Absolutely. Reliability is key.
And that requires rigorous testing and optimization.
Right.
To ensure that these devices meet the highest standards of performance and reliability.
We can't cut corners when it comes to safety and reliability.
It's a reminder that scientific progress is a marathon, not a sprint.
It is.
It takes time, effort, and collaboration to turn groundbreaking discoveries into technologies that can benefit society.
It's a long and winding road, but it's worth it.
And this journey of discovery is filled with both challenges and opportunities.
It is what makes it so exciting.
It's a journey that requires us to push the boundaries of our knowledge.
To think outside the box.
To think creatively. And to work together to solve complex problems.
It's a collective endeavor.
It's a journey that I, for one, am incredibly excited to be a part of.
Me too. It's an honor to be involved in this kind of groundbreaking research.
And for our listeners who are eager to join us on this adventure, where can they go to learn more? What resources would you recommend?
There are some fantastic resources available online.
Okay, like what?
A great place to start is the website of the Rice University Research Group that conducted this study.
Okay.
They have published several papers and articles that explain their work in more detail.
Excellent recommendation.
Thanks.
And for our listeners who are interested in the broader field of quantum materials, are there any other websites or organizations that you would suggest checking out?
Absolutely.
What would you suggest?
The Institute for Quantum Information and Matter at Caltech has a wonderful website that provides a wealth of information on quantum materials and their potential applications.
Those are some great starting points.
I hope so.
And of course, there are countless books and articles.
Tons.
On quantum mechanics.
Yeah.
Superconductivity and spintronics.
So much to explore.
For those who want to delve even deeper.
Right, if you really want to get into the weeds.
But remember, even the most complex scientific concepts can be broken down and understood.
It can.
With a little bit of effort and curiosity.
That's right. It's all about asking questions and seeking answers.
Exactly. Don't be afraid to dive in and explore.
Jump in the water's fine.
You might be surprised at what you discover.
You never know what you might find.
Well said.
Thanks.
And who knows?
Yeah.
Maybe one of our listeners will be the one to make the next breakthrough in Kagome magnet research.
That would be amazing.
That would be incredible.
It would be a real game changer.
But for now, we've reached the end of part 2 of our deep dive into the fascinating world of Kagome magnets.
It's been a great discussion.
In the next and final part, we'll step back and consider the bigger picture.
The big picture.
Exploring the potential societal impacts of these technologies.
Right.
And what the future might hold for this revolutionary field of research.
The future is bright for Kagome magnets.
So stay tuned for part 3.
We'll be right back.
Welcome back to our deep dive into Kagome magnets.
Glad to be back.
We've explored their unique properties, the groundbreaking research on Eisen, and the potential for revolutionary technologies like high-temperature superconductors and quantum computers.
It's been a whirlwind tour of the quantum realm.
Now it's time to step back and consider the bigger picture.
Okay, the big picture.
We've been focusing on the what, the science, the discoveries, the potential applications.
The nuts and bolts.
But now we need to shift our focus to the so what.
So what?
What does all of this mean for society?
Right, the implications.
What are the potential implications of these advancements?
That's the million-dollar question.
That's a great point. It's easy to get caught up in the excitement of scientific breakthroughs.
It is. It's easy to get lost in the details.
But it's crucial to consider the broader context and the potential impact on our lives.
Absolutely. We need to think about the big picture.
Exactly, and that's where things get really interesting.
Okay, tell me more.
Because the potential implications of Kagome magnet technology are vast and far-reaching.
They touch on everything.
They touch on everything from energy and transportation to healthcare and information technology.
It's mind-boggling when you think about it.
So where do we even begin?
Good question.
Let's start with energy.
Okay, energy.
We've talked about the potential for high-temperature superconductors to revolutionize our energy infrastructure.
Right, the holy grail of energy efficiency.
What would that look like in practice?
Imagine a world where we can transmit electricity with virtually no loss thanks to superconducting power grids.
Okay, no more energy loss.
Think about the implications for renewable energy.
Okay, renewable energy.
We could harness solar and wind power in remote locations and transmit that energy to cities with incredible efficiency.
It would be a game changer for the fight against climate change.
It would be a huge step towards a more sustainable future.
And it's not just about large-scale energy transmission.
No, it's not.
Superconducting materials could also revolutionize energy storage.
Right.
Making electric vehicles more practical and enabling the development of more efficient batteries for a wide range of applications.
Exactly. We could power our world with clean energy.
So we're talking about a future with cleaner, more sustainable energy powered by Kagome magnets.
That's the dream.
It's an incredible vision.
It is a vision worth striving for.
And the potential benefits don't stop there.
Oh no, there's more.
Let's move on to transportation.
Okay, transportation.
We've already mentioned levitating trains.
Right, those futuristic trains.
But that's just the tip of the iceberg.
Just the beginning.
Okay, what else is in store for us in the realm of transportation?
Imagine cars and planes with superconducting motors and generators, making them incredibly efficient and reducing our dependence on fossil fuels.
Wow. So we could fly and drive without polluting the planet.
That's the idea.
Or picture a world where high-speed transportation systems connect cities across continents, all powered by superconducting magnets.
It would revolutionize travel as we know it.
It sounds like something straight out of a science fiction movie.
It does, doesn't it?
But it's amazing to think that these futuristic technologies could become a reality thanks to advancements in Kagome magnet research.
It's a testament to the power of human ingenuity.
That's right. And then there's the field of healthcare.
Healthcare, yes.
We've already touched on the potential for Kagome magnets to improve MRI technology.
Right, those powerful magnets.
But the implications go far beyond that.
Oh, much further.
What other healthcare advancements could we see with the development of Kagome magnet-based technologies?
Imagine new medical imaging techniques that allow doctors to see inside the human body with unprecedented detail.
Wow.
Enabling earlier and more accurate diagnoses.
That would be a game changer for so many patients.
We could catch diseases in their earliest stages.
Or think about the potential for developing new drug delivery systems that use tiny magnetic particles to target specific areas of the body with incredible precision.
Delivering medicine exactly where it's needed.
So we're talking about not just improving existing medical technologies, but also creating entirely new ones, all thanks to the unique properties of Kagome magnets.
Exactly. We're talking about a whole new era of medicine.
Precisely. And let's not forget about the potential impact on information technology.
Right. Information technology.
We've talked about quantum computing.
Those superpowered computers.
But there are other exciting possibilities as well.
Oh, yeah, there are.
Okay, take us further down that rabbit hole.
So down the rabbit hole.
What other information technology advancements could we see with Kagome magnets?
Imagine new types of sensors that are incredibly sensitive and precise.
Okay, super sensors.
Capable of detecting everything from minute changes in temperature to the presence of specific molecules.
So we could monitor our environment and our health with incredible accuracy.
Exactly.
These sensors could revolutionize fields like environmental monitoring, medical diagnostics, and industrial process control.
We could gather data like never before.
So we're talking about a world where we can gather and analyze data with unprecedented accuracy in detail, leading to advancements in countless fields.
It would transform our understanding of the world around us.
Exactly. And as we develop a deeper understanding of Kagome magnets and learn to control their properties, who knows what other applications we might discover?
The possibilities are truly endless.
It's truly an exciting time to be alive with so much potential for innovation and progress.
I agree. It's an incredible time to be a scientist.
But as we navigate this uncharted territory, it's important to do so thoughtfully and responsibly.
Absolutely. We need to be mindful of the potential consequences.
You're absolutely right. We need to ensure that these advancements benefit society as a whole, not just a select few.
That's the key. It's about using these technologies for good.
And that means having open and honest conversations about the potential ethical implications and societal impacts of these technologies.
We need to have those tough conversations.
Okay, let's talk about that.
Right.
What are some of the ethical considerations that we need to keep in mind as we develop Kagome magnet-based technologies?
Well, one major concern is the potential for job displacement.
Job displacement, right?
As these technologies automate various tasks and processes, it's important to think about how to support workers who may be affected by these changes.
That's a valid concern. We need to ensure that technological progress doesn't leave anyone behind.
I agree. We need to find ways to help people adapt and thrive in this new world.
And then there's the issue of access and equity.
Right, access and equity.
We need to make sure that these technologies are available and affordable to everyone, not just those who can afford them.
Everyone should have the opportunity to benefit from these advancements.
It's about ensuring that the benefits of these advancements are shared by all, not just a privileged few.
Exactly. It's about creating a more equitable society.
And then there were concerns about privacy and security.
Privacy and security, yes.
As we develop increasingly sophisticated technologies, it's crucial to consider how to protect personal data and prevent misuse.
We need strong safeguards to protect our privacy.
Those are all valid concerns.
They are complex issues, but they are issues that we need to address.
It seems like we're at a crossroads where we have this incredible opportunity to create a better future, but we need to do so carefully and thoughtfully, considering not just the technological advancements themselves, but also their broader societal implications.
I agree. It's a balancing act.
You're absolutely right. We need to have open and honest conversations about the potential risks and benefits of these technologies involving not just scientists and engineers, but also policymakers, ethicists, and the public at large.
We need to have a societal conversation about these technologies.
It's a reminder that scientific progress is not just about making discoveries, but also about engaging in dialogue, considering different perspectives, and working together to create a future that benefits everyone.
It's about using our knowledge wisely and ethically.
Well said. So for our listeners who are eager to stay informed and engaged in this conversation, what can they do?
How can they stay involved?
Where should they go? What resources would you recommend?
There are many ways to get involved.
Okay, such as?
Follow the work of research groups and organizations that are at the forefront of Kagome magnet research.
Okay, like the Rice University group we talked about.
Exactly, and there are many others out there.
Read articles and books on the topic.
There's a wealth of information available.
And most importantly,
yes, this is key.
Engage in conversations with your friends, family, and community about the potential impacts of these technologies and how we can ensure that they are used responsibly and ethically.
It's about raising awareness and having those important conversations.
Those are great suggestions. We need to be informed, engaged, and proactive in shaping the future that we want to create.
We all have a role to play.
Absolutely. And as we conclude our deep dive into the world of Kagome magnets, I want to leave our listeners with a final thought.
Okay, final thought.
The discoveries we've discussed today are just the beginning.
The tip of the iceberg.
There is so much more to explore, so much more to learn, and so much potential to unlock.
It's an exciting time to be involved in this field.
The future is full of possibilities, and Kagome magnets may very well be the key to a brighter, more sustainable, and more technologically advanced world.
I believe they are the key to a better future.
It's a future that I, for one, am incredibly excited to witness, and I hope that our listeners will join us on this journey of discovery as we continue to explore the fascinating world of science and its impact on our lives. Thank you for joining us on this deep dive into the world of Kagome magnets.
It's been a pleasure.